Hey everybody, this is our lecture on section 3.4, which is the last section for the material on exam 1. So in section, we didn't cover it, okay, but let me tell you what one of the results of section 3.3 is. I don't want to cover it explicitly because we're going to cover something in more general detail later. There's no point going over the same thing too many times. Actually, we're going to cover it several times in more detail. But in section 3.3, and you've also covered something in Calc 2 like this, it is shown that the length of the curve r of t, or a less than or equal to t less than or equal to b, is, well, it's just like what it was in Calc 2, although we didn't state it this way. It's the integral from a to b of the length of r of t dt. And that would be, this curve that's, being drawn by r of t, going in a certain direction. So t equal to a, t equal to b, and this is r of t. So in 2 dimensions, this is equal to integral from a to b. So what's r prime? It's x prime of t squared, because we're doing the length, y prime of t squared dt. So in 2D, it looks like that. So let me put that all in one line. So in 2D, it's this. And in 3D, it looks like this. There's just the added z component. Like that. All right. So that should look more, or z prime of t, excuse me. That should look more familiar to you from Calc 2. Now, what is the importance of this? Okay, since that's the length of the curve. So if we therefore think of r of t, or of t, as time measured in some unit, seconds, minutes, hours, etc., and r of t as position, in 2D or 3D space, okay, then what happens? Right, the length traveled, which is the integral from a to b of r prime of t dt, sorry, not length, but the distance traveled is equal to this. And instead of having a b, we'll have, say, a parameter x. Distance traveled for a less than or equal to t less than or equal to x. Therefore, if you take distance traveled, derivative with respect to time, what do you get? Since the derivative with respect to time, I guess we shouldn't use x. X is bad in this case. TS, call it S. Since the derivative with respect to time of distance traveled is speed, we now get that. Actually, let me put the S here. S. Oh, how should we say it? Just B is fine. T. Since the derivative with respect to time of distance traveled is speed, we now get that the derivative of the integral a, b, the integral function, a, b, r prime of t dt is speed, right? The derivative of the integral function is speed. We now have that. Well, the derivative of the integral is just the function back again, right? Because they're reverse operations of each other by the fundamental theorem of calculus. We get that the length of r prime of t is the speed of travel of the particle over time. Okay, so in a one-dimensional context, that's much more obvious. But here we're talking in 2- and 3-dimensional contexts. Okay, t is time measured in some unit, and r of t is position in 2D or 3D space. So the length of the curve is equal to distance traveled. Right, which is the integral from a to b of the length of r prime of t dt for t between a and b. And the derivative of distance traveled with respect to time is speed. So the derivative of the integral, which is this, is speed. So, in summary, the following make physical sense. Right, t is time, r of t is position, the length of the derivative is speed. So what is the derivative itself? It's the speed given a certain direction. That you call it velocity. All right, t is time, r of t is position of a particle traveling through time. R prime of t, length of r prime of t is speed. And therefore, the vector quantity, which has got magnitude, which is speed, and a direction, which is tangent to the curve, that must be velocity. And r double prime of t, acceleration. This last one needs a little bit more explanation, but we'll leave that out. So when you're talking about motion in space, these vector functions, they provide really the most general kind of situation that you want. In Calc 1 and 2, you only talked about the speed of an object traveling along a line, or the position of an object traveling along a line. Everything was along a straight line. Except once in a while you would talk about like, I don't know, the arc. You throw a ball through the air, and it would follow some arc of travel. I think that's covered in Calc 1 or Calc 2, but mostly it's just a linear path of travel. So now you have just a general trajectory through space. Could be in 2D space, 3D space, whatever you want. Okay, so this is the most general situation, and it requires this multivariable calculus that we're taking now. But it's not too much more. It's not too much more complicated than what was studied in Calc 1 and Calc 2. Interesting example here. Let's see. Okay, if you had r of t is equal to cosine t sine t, right, for t bigger than or equal to 0, then this is talking about, travel along a circle, the unit circle in the counterclockwise direction. Circle of radius 1. It could be a circle of any radius. K cosine t, k sine of t, like that, in which case it would be circle of radius k. So in this case, r prime of t is equal to minus k sine of t, k cosine of t. So the speed is equal to the square root of the square of these things, k squared sine t, plus k squared cosine t, right? So this is equal to, right, factoring out the k squared, sine squared t, cosine squared t, these are squares. This is just equal to 1. So the whole thing is just equal to k. Units of distance per unit of time. Unit distance over unit time. So this method of describing travel along a circle gives you a constant velocity, and that velocity increases with the bigger the circle is. Why does that velocity increase with the bigger the circle is because what? The t represents an angle, right? This is the angle t. So t is increasing at a rate of 1. Radian per second, radian per hour, radian per minute. So the angular speed is a constant. It's just 1. But if your angular speed is constant, any of you that have ridden those old merry-go-rounds at the playground, anyone knows when you're closer to the middle, you don't move as fast. When you're closer to the end, boy, you're really whipping around there pretty fast. When you're still, turning that merry-go-round in a similar speed that was being turned before. So we've all, probably most of us have experienced that. So this description of circular travel gives you a constant speed. Similar to that would be ellipses, elliptical travel. So let's say 3 cosine t, 2 sine t. So this is the ellipse, right? 3 units in the x direction, 2 units in the y direction. Let's see. Not quite good enough. All right, so we're traveling along the ellipse in the counterclockwise direction. What kind of speed do we have now? All right, this is t equal to 0, t equal to pi over 2, t equal to pi, t equal to 3 pi over 2, and then t equal to 2 pi, you're back here. What kind of speed do we have here? Well, r prime of t is minus 3 sine t, comma 2 cosine t. So the speed is equal to 9 cosine or sine squared plus 4 cosine squared t. Right? Well, this is equal to, so 9, of course, 9 sine squared gives me 5 sine squareds plus 4 sine squareds plus 4 cosine squareds. This is just equal to 4. So 5 sine squared t plus 4. All right, so where along the ellipse is the speed the fastest, and where along the ellipse is the speed the slowest? Well, sine squared t sine is between -1 and 1. So sine squared is between 0 and 1 because when you square it, it becomes positive. Right? Where is sine equal to 0? It's equal to 0 at 0 degrees, or 0 radians, pi radians, 2 pi, 3 pi, 4 pi, 5 pi, right? At whole multiples of pi. And it's equal to 1 at half multiples of pi. So when the radius is the smallest, when we're traveling up through here, the velocity is the fastest. And when the radius is the highest, that's when the velocity or the speed is the slowest. So at t equal to 0, pi, 2 pi, 3 pi, etc., speed is equal to square root of 4, which is 2. And at t equal to pi over 2, odd multiples of pi over 2, 5 pi over 2, 7 pi over 2, etc., speed is 4 plus 5, right, which is equal to 3. So speed is the slowest when the radius is, when you're at the larger radius of the ellipse, when you're out here and out here, and it's the fastest when you're at the shortest part of the radius of the ellipse. Right? And, elliptical travel, is something that, goes into the study of orbital mechanics, right? When you're looking at one orbit, one body, in space orbiting another body in space. I mean, these orbits are often elliptical in shape, more so than circular, or like slightly elliptical. So these types of analyses come in handy in those situations. What other type of examples? Remember the helix? So that was example number 2. Example number 3, let's look at the helix. So r of t equal to cosine t, the circular helix, sine t, t. And let's also look at this. R of t equal to cosine t, sine t, 1 over t. Okay? So this represents two paths along the helix, which lives on the cone or cylinder of radius 1. Okay, let me copy that. So this first one, right, cosine t, sine t in the x and y coordinates, it again just, tells us we're moving in a circle in the counterclockwise direction for just x and y. But then the z is going up in a linear fashion. So looking like this. Right. And here, what's going on? Well, the z looks like that. Right, 1 over t. So here's z, here's t. 1 over t is equal to z. So we're doing this in the z direction, and yet we're still going in a circle in the counterclockwise direction for x and y. So what goes on is something like this. Like that. So what do we have for speed? Actually, let me leave that picture there. Here, speed is equal to the length of r prime of t, which is, well, the derivative of this is minus sine squared, it's just sine squared t. The derivative of this is cosine squared t. The derivative of that is 1. So you just get 1. So this is square root 2. So speed is constant. Speed is constant for this standard helix. But for this one, speed is equal to the length of r prime of t, which is sine squared t cosine squared t. Now, the derivative of 1 over t is minus 1 over t squared. So this is minus 1 over t squared squared. So this is equal to 1 over t to the 4th. All right, so for t less than 1, say, for 0 less than t less than 1, right, the speed is large. And then for t approaching infinity, speed approaches 1. All right, so for large values of t, this is close to 0. So the speed is about 1. And then for very small values of t, close to 0, this is a really huge number. So you have very large speeds. So here we're traveling very fast as we come down this, but then it just kind of slows down and approaches more or less constant speed. Okay? So those are pretty interesting examples. One other interesting sort of example that you could have is the following. Let's talk about acceleration a little bit. And Newton's second law. Given a path traveling along the curve, particle a point or something like that. So I mean something, small, or the center of something large, the center of mass of something big. So I mean if you want to talk about a point traveling through space, I mean that point could be a point, or it could be just some larger object and that point is the center of mass. There's a couple different ways of thinking about that. So given a point traveling along the curve r of t, again where t is time, acceleration, right, a of t is the second derivative of r of t. Newton's second law right, that force is equal to the force acting on an object on that traveling object, acting on that traveling object, satisfies force is equal to mass, right, which is just some constant quantity typically, times A of t, right? So 1 over the mass times the force is equal to the acceleration vector function. Since force is something you can measure, as well as mass, this yields a method of finding the acceleration function. Right? And once you know the acceleration function, knowing A of t, which is r double prime of t, and knowing what your initial velocity is, v0, we can calculate using antiderivatives v of t, which is r prime of t, using antiderivatives. Then, if we know the initial position, r0, we can then calculate position. R of t. So that's, a notion of how one can keep track of where an object is as it's traveling through space, right? Since you can measure acceleration, right, because acceleration is going to be proportional to the force acting on the object, and you can feel the magnitude and direction of the force, that means you can calculate acceleration. And then if you know your initial velocity, maybe 0, then you can use antiderivatives to calculate velocity. And then knowing your initial position, 0 or something like that, then you can calculate your position, r of t at time t. So that's theoretically a way one can keep track of position while traveling through space. Okay? And we covered doing antiderivatives in the last section. Okay, so that is the end of the lecture on section 3.4.